Have you ever looked at the world around you and felt like the universe is speaking a language you just don't quite understand? From the way a planet spins to the speed of light, there's a kind of hidden logic to absolutely everything. Well, today, we're going to learn the vocabulary and the grammar of that language, the language of physics. Let's get right into it.
I mean, that's a huge question, right? Where do you even begin? How do scientists possibly manage to describe something as massive as a galaxy and something as tiny as a single atom using the same set of rules? Well, it all comes down to having a shared language.
And just like any language, it all starts with the basic vocabulary. Before you can write sentences or tell stories, you need to know the words. In physics, these fundamental words are what we call physical quantities. They are the essential building blocks we use to measure and describe everything.
So, what exactly are these words of physics? Let's take a second and break down what a physical quantity actually is.
It's actually pretty straightforward. A physical quantity is anything you can measure. Yep, that's it. If you can put a number on it, whether you're using a ruler, a stopwatch, or even a complex formula, then you're dealing with a physical quantity. You are officially speaking physics. Think of this table as our Rosetta Stone for physics. On the left, you've got the quantity itself, the concept, like length or mass. In the middle, you have its official scientific unit, what we call the SI unit, like meters or kilograms. And over on the right, you've got the tool you'd use to measure it. These are really the basic nouns of our new language.
Okay, time for a little pop quiz. Let's test your fluency. Take a look at this table. Which one of these quantities is matched up with the correct unit? I'll give you a second. Got it? The answer is B. Latent heat is a form of energy, and energy is measured in joules. Hey, nice work if you got that one right.
So, we have our basic words down, but how do we use them to talk about things that are incredibly big, like a galaxy, or unbelievably small, like an atom? That's where prefixes come into play.
This is where the language gets its incredible range. You see, instead of saying a galaxy is billions upon billions of meters away, we use a simple, much more elegant tool. Prefixes. They're like little multipliers that scale our basic units up or down to keep the numbers nice and manageable.
And here's how it all works. Each one of these prefixes is just a shorthand for a power of 10. So kilo means 1,000. A kilogram is just 1,000 grams. Milli means 1,000th, so a millimeter is just 1,000th of a meter. It's a beautifully simple and powerful system that stops our numbers from getting ridiculously long.
Okay, let's put this into practice. Let's say we have 12,000 grams. How would we express that a little more neatly using kilograms? Think about the prefix.
The process is actually super simple. First, we know that kilo means 1,000. Now, the key rule to remember is this. To add a prefix to a number, you divide by its value. So all we have to do is take our 12,000 grams and divide it by 1,000.
And there you have it, 12 kilograms. See how much cleaner and easier that is to work with? That is the real power of using prefixes. It's all about making the numbers make sense. All right, now that we can handle both huge and tiny numbers, let's talk about the tools that let us get those measurements in the first place. Because in the world of physics, precision is absolutely everything.
Now, check this thing out. This is a micrometer screw gauge. It's an instrument that is designed for extreme precision. It's perfect for measuring something as thin as a single strand of wire, or even a sheet of paper with incredible accuracy.
So how do you actually read one of these? It might look a little complicated, but it's really just two scales. First, you look at the main scale on the sleeve. In this example, we can see the 2.5 millimeter mark is the last one visible. So that's our first number. Next, we look at the rotating thimble scale. We just find the line that lines up perfectly with the main scale's center line. In this case, it's the number 36. Now, each of these marks represents 1/100th of a millimeter, so that gives us 0.36 millimeters. And finally, you just add the two readings together. 2.5 plus 0.36 gives us our final measurement of 2.86 millimeters. Now that is some serious precision. So why does any of this matter? Well, that tiny fraction of a millimeter we just measured, that's the difference between a high-performance car engine and, well, a catastrophic failure. Precision engineering, which relies on tools just like this, is quite literally all around us.
Okay, so we've learned the words. Now it's time for a little bit of grammar. You see, not all quantities are the same. Some of them carry an extra piece of information that is absolutely crucial: direction. This is a really fundamental distinction in physics. On one hand, you have scalars. They're simple. They just tell you how much of something there is. Think about your speed on the highway or the mass of an apple.
But on the other hand, you have vectors. They're a bit more sophisticated. They tell you how much and which way. It's not just how fast you're going, but where you're going. It's not just a push, but a push downwards. That extra bit of info about direction is critical.
Now, since vectors have direction, you can't just add them together like regular numbers. Nope. There's a special technique, a kind of art, for figuring out their combined effect. So let's imagine an object that's being pulled by two different forces at the exact same time. We'll represent them with these two arrows, force X and force Y. The big question is, how do we figure out which way the object is actually going to move?
We use a really simple graphical method called the head-to-tail rule. All you do is you take one of the vectors and you just slide it over without changing its length or its direction, so that its tail or its start touches the head or the arrow end of the other vector.
And here's the final step. You draw a new arrow that starts at the very beginning, the tail of the first vector, and ends at the very end point, the head of the second vector. This new arrow, which we call the resultant, represents the total, combined effect of those first two vectors. It's the net result of all the forces acting on that object. All right, time for one last challenge. Take a look at forces X and Y. Which arrow, A, B, C, or D, shows the correct resultant force? Take a second. If you imagine completing a parallelogram with these two vectors as its sides, the diagonal that starts from the same point gives you the answer. So, the correct answer is A. Nicely done.
And there we have it. We've covered the absolute fundamentals. The quantities, the units, the prefixes, the tools, and even the basic grammar of scalars and vectors. You now have the foundational toolkit you need to start describing the physical world with real clarity and precision. So the only question left is, what will you choose to describe first?